Swayam Prabha. Digital India. Educated India.
Okay guys, so let's focus, let's come back. So you might have heard a lot about quantum computing and Google and IBM doing amazing things with qubits and things like that. So I'm going to give you some overview of what is all this hype about, why should we care about quantum technologies and so on. Have you already had a talk during this program on something to do with quantum physics? Many things? Okay, so I hope you won't be bored by what I have to say. Okay, so I have a little bit of introduction on why we should care about quantum technologies in general, but I want to quickly go on to the hardware, right? So what I mean by that is, if I ask you to implement a very complicated calculation, let's say I want you to factorize a very large number, okay? So there are two aspects to this. One is you pick your favorite programming language and you write a code, in Python or C or C++, and you write a code for this. But there's another thing that you very rarely see in at least school computer science or even first year college computer science, which is what actually happens under the hood, right? You send this to this machine and there's something going on there that enables that device to give you the answer for your question, right? So and that is hardware, okay? So for every computation we do, there is the software and the algorithm side of things, which is what we normally attribute as computer science in school, at least. But then there's also the hardware aspect where we really have to understand at the level of silicon, right? At the level of the chip, what's really going on? What are the transistors doing, right? And today's talk is somewhat like that, but not for the computers that we are used to, like this laptop or my iPad or something like this. It's more about how quantum hardware is realized in practice. Okay, how do some of the leading quantum technology platforms operate? What are the physical principles? How does all this quantum mechanics, whatever you have heard of, over the last few days, how does it actually lead to our ability to do better computations and so on, right? So that's what the talk is mostly going to be about. So let's see. So let's begin. So like I said, one thing is that we live in a largely digital world, okay? A lot of the technologies we use are basically things that deal with zeros and ones. So for example, this is our favorite Intel processor. We process bits, we store bits, right? And even things like smart TVs and phones and so on, all of these also work on the concept of zeros and ones. And of course, the entire AI revolution, do you know what this is the logo for? Very good. So everyone seems to know it. Okay, good. So now even washing machines have artificial intelligence. Sometimes I wonder if it's smarter than me, right? So even these kind of devices, which you normally don't think of as having some computing power, are now being equipped with computing power. Okay, that is the ability to process and do some kind of task, make some decision based on the ability to ultimately process zeros and ones. Okay, so we live in a very digital world. Okay, and basically the idea is that the two sides of a coin basically give us two different pieces of information. Okay, 0 or 1, and this is what we usually call as a bit. Okay, so any piece of information we can basically convert into a stream of zeros and ones, and we can use this to encode that piece of information. For example, as simple as taking a decision to bat or bowl first. Okay, it begins there, and it begins. Okay, that's okay. Well, so it begins there and goes on to more and more complicated tasks as well. Okay, so in a way, this is kind of natural to us because when we toss a coin, we expect that it will land as a head or a tail, right? And then you're either present or absent to a class, and well, we'll soon find out whether this will happen or not, right? Finally, so at least they've qualified, so they will either win IPL 2025 or not. Okay, so it's one way or the other, and this is kind of aligns with our natural intuition. Okay, so something like my water bottle, it's there or not there, it's empty or full, right? So this kind of thing aligns with the way we view our classical world. And if you have more than two possible states, like say a die, sorry, then it has six possible outcomes. And what you can do is introduce a stream of zeros and ones, okay? And then you have the six different outcomes, and you can encode basically 0 as 000 and keep increasing, the one count, basically put it in the least significant bit, then in the next one, and so on. And you can keep encoding more and more states of the die into this, into basically a stream of 3 bits. Okay, and you can pick 6 of those combinations to encode the 6 possible outcomes of a die. By the way, this is also the logo for our technical festival at IIT Madras. Although I don't know why they have the same number on all sides of the die. So something we can ask them, right? So, and the point is, this intuition does not always work. Okay, so as we go to smaller and smaller length and energy scales, we quickly see that a lot of our intuition begins to fail. Okay, and one important concept that arises in quantum mechanics is the concept of superposition. That means that if I have two well-defined states, it is indeed possible for a very small atomic scale system to actually be in a superposition of two different well-defined states. Okay, so something like what I'm showing here using Bulbasaur and Ivysaur, if you ever followed Pokemon, right? So the point is that as we go to smaller and smaller scales, we have to redefine our intuition, and at first sight it may be a bit worrying. Okay, oh, things don't work as I expect them to. But if you think more carefully about it and what are the implications of the principles of quantum mechanics, you quickly realize that it actually gives us a very new and fundamentally different way of processing information. Okay, so basically over here I want to introduce you to the concept of a qubit. Okay, so and the analogy I want to give you is that let's think of the XY plane. So normally with a coin, you think of 0 and 1 as two distinct outcomes. And with quantum mechanics, what happens is, this is not a perfect analogy, so you should take it, more like, it's not a one-to-one mapping, it's more like an analogy that I'm trying to give you. It is almost as if 0 and 1 are like two different axes. Okay, so it's like this is a 0 axis and this is a 1 axis. Okay, so you can think of this as unit vectors x hat and y hat. Okay, for example. Okay, it's not as simple as that, but for the moment it helps to build intuition. Okay, and then the state of a system is not just 0 or 1, it can actually be some vector, some unit vector that lies in this 0 1 space. Okay, and I say space because you have, again, in a two-dimensional plane, you can think of it as two-dimensional space, a three-dimensional world as a three-dimensional space, and so on. So you can basically have some superposition, or this is what we can roughly think of as a superposition. That means that this vector has some projection onto 0, but also some projection onto the vector 1 as well. Okay, and typically in quantum mechanics, especially in quantum computing and so on, the way these vectors are represented are basically as 0 and 1. Okay, this is called a ket. Okay, and we won't go into too many mathematical formal details of this. I just want you to take home the idea that this entire concept of linear algebra and vector spaces, okay, underlies the entire mathematics of quantum mechanics and and it kind of explains very well how the microscopic world behaves. Okay, so, and now what we have here is essentially kind of a quantum coin, right? It has a state 0, it has a state 1, but now the state of the coin is not just 0 or 1, it is some vector, and on top of it, so let's write a general vector, right? So let's write it like this. Okay, and this is basically some state of the quantum coin that we are talking about. Okay, think of it like, the analogy again is that any position vector in the xy plane can be written as some combination of x hat and y hat. So somewhat similar to that. Okay, but then there is a crucial difference between the example I gave you and quantum mechanics. One of them is that physical states are unit vectors. Okay, so they have to be normalized. Okay, and on top of it, this A and B are all can be complex numbers. Okay, so they need not be real numbers like a position vector in the xy plane. So what you have is actually a complex vector space and complex vectors associated with it. Okay, so what we have is a normalization condition. Okay, and the way the normalization is defined is that, are you guys familiar with complex numbers a little bit? You are? Okay, so the way the normalization is defined is written down is mod a square plus b square must be 1. Okay, so that's one condition, that's the normalization. So what I want you to tell me is, just think about it for a second and forget this part. Without this, how many real numbers do I have to specify the state psi? Okay, without any constraints. Can you think of it? So I haven't given you this yet. I've only given you that any vector can be written like this, where A and B are complex. So how many real numbers do I need? I said A and B can be complex. 4, right? Because you have A can be written as some, A real plus I A imaginary, and B can be written as B real plus I B imaginary, right? So that's basically 4 complex numbers to begin with. Okay, but then do you guys also know the polar representation of complex numbers, right? So I can basically write this as some mod A e power I, let me call this phi, okay, phi A, and this I can write as mod B e power I phi B, right? So now I have basically again 4 numbers, 2 moduli and 2 angles, okay, to specify this. Okay, and it turns out that quantum states are defined only up to a global phase. What that means is that a state psi and a state some e power theta psi, okay, these two are basically one and the same. Okay, there's no, what I mean by that is, no matter what measurements you do on a state like this, we'll come to measurements, but basically a state that can be described by psi can equivalently be described by a state that looks like e power I theta multiplying psi. That basically means multiply this whole thing by some phase. Okay, so based on that, what can you say about the number of free parameters I need to specify given this constraint here? That 2 states with a global phase multiplying it are equivalent, right? So what does that imply about the right now we had 4 parameters. What would this imply? Do you really need 4 parameters? All the angles? Why would it reduce 2 parameters? Any reason? So why don't you write it down? So write down a state that looks like, write this down with a modulus and a phase. Just write it down on a notebook if you have. And what I'm asking you to do is take out a global phase. Okay, so factorize out some global phase. Let's try to do that. So write down a state. What does a global phase mean? So a global phase is basically that I have the state here, right? So I'm telling you that I can multiply this with any exponential of this form, e power I theta, right? This is the polar represent, anything like this, and so I get a new state which looks like e power I theta a0 plus e power I theta b1, right? This basically multiplying the coefficients. And my point is that this state and this are equivalent. This phase does not really change anything about the system. I'm telling you that, just believe me, okay? So I'm not giving you any explanations for that. But given that, okay, if you're given that, I want you to tell me how many parameters are actually needed. Do you really need 4? Wait, who's talking? I can't find. Okay, sorry. So say that again. you can only remove one angle globally, right? So let's write this out, okay? So let's take this, and I'm going to basically take this and plug it in here, okay? So what you will have is a state that looks like okay, that's what I have. And what I'm going to do here is I can make a choice, okay? It doesn't matter what phase I pull out, okay? I can make a choice. So I'm going to pull out e power I phi a, okay? So what that means is I'm going to write this like this. That's the mod. And then here I'm going to write this as phi b minus phi a, okay? And so, as I said, because psi and e to the I theta psi are essentially the same state, I don't need this to specify the state of the system, right? So all I need is what is called a relative phase. Okay? So I need to only specify what's the relative phase between the state 0 and 1. Okay? And in terms of the xy plane, this is something like you can have a vector that looks like x hat plus y hat, but you can also have a vector that looks like x hat minus y hat, right? Both of them have equal weight on the x and y axis. It's 1 and 1, but then the relative phase is pi, right? So one vector actually points x hat plus y hat would point like that, and x hat minus y hat would point like that, right? So and clearly those are two different distinct states. Yes.
Axis as the 0 state and the 1 state. So since we are anyway taking projection on the axis, does the modulus really matter? Because anyway what we are concerned with is how much it falls on the axis.
No, but the phase matters, and we'll come to that. And the point is that even so this is not a direct analogy to how you represent a quantum state. You should really represent it like that. We'll come to that in a second. But even on the xy plane, right, I could define, let's say that this is not 0 and 1, this is more like x-axis and y-axis, okay? Then I could have two vectors like this which have equal projections in terms of the modulus on the x and y-axis. It's always the same, but then they're clearly two different vectors, okay? And this difference comes because one of them, you can think of it roughly as x hat plus y hat, and the other is basically x hat minus y hat. Right?
Yes. So here we are anyway consider, you say the phase is the angle, right?
Yeah.
Yeah, so the angle only matters by now. Why do we need a modulus?
Why do you? Oh, because I could have another set of states. Okay, and one of them would be, for example, I don't know, 1 by root 2 x hat plus 1 by root 2 y hat. And the other could be, for example, root 3 by 2 x hat plus half y hat, right?
How exactly is the magnitude translating? Because how does it make sense to say I am half 0, half 1, but I'm 1 by root 2 0 and 1 by root 2 1 of this?
So you're asking me how is it that simultaneously I can be in both x and y? Is that what you're asking? No.
That I got. I don't understand what sense does the magnitude make of it. Like,
So let's take extreme cases.
And this much in the same
That's all it means. Yes, and they're unique states.
Difference in magnitude.
It implies, okay. So okay, now you're getting to the heart of what it means for these coefficients, right? So we'll come to that in a second. Okay, so keep that question. If I still haven't answered it in 5 or 10 minutes, come back to me. Okay, so yeah, so right now we have 3 parameters, okay, to specify this. And now I'm going to give you an additional constraint, which is that the state psi has to be normalized like this. Okay, so it's a unit vector. Okay, that's why even in these examples I kind of try to take trigonometric values so that it satisfies this condition. So given this additional constraint, now how many parameters do I need to specify the system? 2. So you basically need one magnitude, okay? So maybe for example mod B, okay? And then mod A is simply given from this constraint, right? It's simply given as 1 minus mod b square, right? And then I have one angle, okay, and what I'm going to do is simply call this angle as phi, okay? I mean, we initially thought we needed two angles, but we only need one angle. So why should I call it phi b minus phi a? I might as well just call it phi, okay? So that's the one free parameter I need to specify in terms of angle and one magnitude, okay? Now, I want you to look at this and tell me what's an efficient parameterization of something that looks like this? What quantities do you know add up? Exactly, right? So angles basically, trigonometric quantities of angles basically add up like this. So instead of specifying mod b, I'm basically going to specify an angle theta, okay? And so I'm going to say that mod a is basically cos theta, and there's a reason I will call this cos theta by 2, okay? It helps. I'll come back to why this by 2 is useful. And then mod b is basically sin theta by 2, and this is sufficient because I needed one parameter, right? But that one parameter I'm now again using an angle instead of some real number, okay? And on top of this I need phi, okay? So
why do these vectors have to be normalized?
the normalization is required. That comes back to his question. The normalization is required because it turns out that basically you take these two numbers here, okay? So the mod square of this number is simply mod a square, and the mod square of this complex coefficient is simply mod b square, okay? E power I phi, when you take modulus it goes away, right? Its modulus is 1, right? So the point is that when I make a measurement on the system, okay, when I want to find out is the state in 0 or 1, the probability of getting an outcome 0 is related to the modular square of this coefficient. That's mod a square, okay? And the probability of getting the outcome 1 is related to mod b square. And these are probabilities. Probabilities have to add up to 1. That's the reason why physical states have to be normalized to 1. Okay, because what you're writing down, so the big distinction between traditional statistics and quantum mechanics is that statistics is usually built on probabilities, whereas quantum mechanics is built on probability amplitudes. Suddenly you have to think about the coefficients here because those coefficients are in some loose sense square root of a probability, because only when you square them you get something that's actually a probability, and those things add up to 1. Okay, and that's why you need, I think that answers your question also, right? So, right, so now I have two angles, theta and phi, right? And these two angles basically are enough for me to represent the state of a two-level system, okay? And I call this two levels because I'm trying to model a quantum coin, okay, where I'm saying that the analogy, the useful analogy to keep in mind is that 0 and 1 are not two states, they're more like two basis vectors, and they can have complex coefficients subject to a couple of constraints. One is that it has to be normalized in a particular way, and you can always pull out a global phase which is irrelevant, okay? Now if I go to more complex, if I want to model a quantum die, I need 6 basis vectors. It's a 6-dimensional space. And you shouldn't get confused with the dimensions of our physical world. This is some internal dimension associated with that quantum system, okay? So it's not directly related to the spatial dimensions that we live in, okay? So anyway, we'll stick with two-level systems for now, and now I have two angles here, okay? So what I can do is basically represent, so one angle is a polar angle, that's this angle that's sitting here, okay, in the populations. So you can think of this as mod a square and mod b squares as populations of the different levels or probabilities, right? And this is the relative phase between them, okay? So you can use theta as a polar angle, okay? So I will mark on a sphere the state 0, okay? That means that when all my probability is sitting in the state 0, right? This coefficient is 1 and this is 0. I would mark that on the north pole of a sphere, okay? And I would mark the state 1 on the south pole of the sphere, and all the other possible combinations of states lie on a unit sphere, okay, that is bounded basically by the north pole being 0 and the south pole being 1, okay. So this representation of a qubit is called the Bloch sphere, okay. So this is a very powerful representation, and this is why I kept saying that this xy plane analogy can only take you so far. It's just to introduce or make you comfortable with the idea of, you know, vectors x hat and y hat, right? But really, because these coefficients can be complex, right, the correct way is to represent it on a surface of a sphere, okay, where the polar angle is basically like a population. It captures the population because it's related to mod A and mod B, and phi is basically telling you the relative phase, okay. So now I wanted to quickly tell me what are the states on the equator. What do they look like? Wait, what? She started first, let her finish. Yeah, go ahead. Oh, everywhere on the equator? Let's try another answer, yeah?
I think it's equal probability of being 0 all.
Right, so theta is the same everywhere, because see, every point on the equator is basically a theta of 90 degrees, right? So now basically I'm saying, given this parameterization, I can basically write my state as cos theta over 2 0 plus e power I phi sin theta by 2 1, okay, that's my state. And you can immediately see that when theta is 90 degrees, this is cos of 45, and that's 1 over root 2, 1 over root 2, and that's equal probability. So every point on the equator is a point of equal probability. It's an in technical language, it's an equal superposition of 0 and 1. And how do they differ? How does one point differ from the other? The state, the phase, the relative phase, right? So the vector along the x-axis is basically a vector that simply looks like 1 over root 2 0 plus 1 over root 2 1, okay, and the vector along the y-axis is basically 1 over root 2 0 plus I over root 2 1, okay. And you can basically, you're familiar with dot products, right? Yeah, so you can basically define something like a dot product. It's usually in this field it's called an inner product. Have you heard that term before? Okay, so it's basically a dot product, and the way you take a dot product of two vectors is that you have say psi 1 is a1 0 plus b1 1, and then you have some other psi 2 which is a2 0 plus b2 1, and the way you so normally when you think of a dot product, what you're doing is you have a column vector and then you have the other vector, you make it a row vector, and then you do a matrix multiplication and you get a scalar, right? So you have something like this, some vector that looks like this, and another vector that you make into a row vector by transposing it, okay, and then this is a 1 cross d dimensional vector, this is d cross 1, and when I take a dot product I get a scalar. That's how you normally do a dot product. These are complex vectors, so the main difference in taking a dot product is that if I'm doing if I'm taking a dot product where I'm doing something like the way it's represented is like something like this, okay, you write it like that, and what that means is for the vector psi 2 I not only take the transpose but I also take a conjugate, okay, because it's a complex vector, okay. So I take a transpose conjugate and that's represented with a dagger, okay. So I want to write this as psi 2 is in some sense psi 2 dagger, okay. So basically this looks like a bracket, right, a total bracket. So this is called a ket and this is called a bra, okay. I mess this up, it should be vertical line. So this is called a ket and this is called a bra, okay. So those are the two things. One of them looks like a column vector, the other looks like a row vector, and you can always take a dot product between a column vector and a row vector, except with the difference that it's not just a transpose, it's a transpose conjugate. So what that means is, here I would do something like A2 star B2 star A1 B1. Okay, that's the matrix multiplication I would do. Okay, and that gives me basically A2 star A1 plus B2 star B1.
Here the dot product is no longer commutative.
It's no longer? Which means if I interchange the order. Yes, you're right. Yes. So psi1, psi2 will give you the complex conjugate of what you get right now. That's correct. Yes. Good observation. Right. Okay. So so one thing you can immediately verify is, if I take psi2 to be equal to psi1, right, then I simply get A2 star is simply A1 star. So I get mod A square plus mod B square, and that is 1, right? So that's basically our normalization condition, and that makes sense also in the picture because every state lies on the unit sphere. So its radius is basically 1. Every state has a magnitude 1. Now I want you to tell me, what about the dot product of two points that are diametrically opposite on the Bloch sphere? Think about it. So let's take this as psi1. Why don't you write down psi2, which is a point that is directly opposite on the diametrically opposite on the Bloch sphere? Can you just write it down? No, I told you that a global phase does not matter. If I just put minus psi, minus is just e power I pi, right? The dot product. No, why don't you write down psi2 first? You will see what it would be. Yes. With what? With everything. Okay. If you can tell me exactly which part confuses you, I can help. So right now what we are doing is, I am trying to get you to appreciate how to take an overlap between two vectors, two state vectors, right? And right now we saw that I am telling you this is how a dot product is defined. A dot product is an overlap, right? And what I want you to tell me is, we already saw that if I take the two vectors to be the same, the dot product is 1. So the overlap of a vector with itself is 1, which is very good. So we are not doing something crazy, okay? Things make sense so far. Can you show that to me? Because normally on the plane, right, when do you have no overlap? When they're perpendicular. But in the spherical representation, I want you to tell me what happens with diametrically opposite points. So why don't you write down, so you know that every state psi which has a theta and a phi is basically mapped onto some point on the sphere, right? So given a theta and a phi, so this particular state, where will you mark it? Well, that's the answer. So basically this is like giving the spoiler before watching the movie, but that's correct. The answer is 0, but I want you to just show me how it would be 0. So I have a point theta comma phi here, right? So a diametrically opposite point would be somewhere there, right? And I want you to tell me what would the corresponding theta and phi values be for that point. Pi minus theta, right? Pi minus theta makes sense because that's 0, this is pi, this is theta, this is pi minus theta. And what about phi? For a diametrically opposite point? Yeah. Phi, yeah, right, you're right. So it basically gets flipped by 180 degrees. So it's phi plus pi, or yeah, phi plus pi is correct. So plug that in and write down an expression for psi2. Okay, so write psi2 as theta prime phi prime, where phi prime is phi plus pi and theta prime is, what did we say, pi minus theta, and use your trigonometric relations. Sorry? Okay. Do you want to write it down? Go ahead. Sure, no problem. The class can help you. Right.
Aren't we supposed to do pi minus theta by 2?
No, the theta itself becomes, yeah, theta itself becomes pi minus theta. The whole thing gets divided by 2. The point is,
Theta by 2 become
because the point is that what maps onto theta here, right, is written there with a theta by 2 inside the trigonometric function. So what maps onto pi minus theta should be written there with pi minus theta the whole divided by 2.
so it should be pi minus theta.
No, right?
So if the theta by 2 is
No, right? Because it's the point that's diametrically opposite to that point is the point with theta replaced with pi minus theta. The whole theta, wherever theta appears in your expression, you replace that with pi minus theta. It's
oh okay,
right.
Okay.
Yeah. So, okay, what do you know about e power I pi? So, simplify it. Not there. Yeah, you're not there. E power I pi, the whole thing becomes minus 1 downstairs. Yeah. Yeah. And then what was remaining? Yeah, write that out. You need the e power is still there, right? So yeah, I with an I, e power I phi, right? Very good. So you can remove the minus 1 because it doesn't. It's just a multiplication, right? So it's just put a minus sign. All right. Okay. Thank you. So I think that's correct. So that's psi 2, basically a point that's diametrically opposite on the Bloch sphere. Okay. So what you can do now is use psi 2, right? You have A2 and B2 basically. So this is psi 2 is now a column vector A2, B2, where A2, B2 are given by these two complex numbers. Well, one of them is real, the other is complex, right? And you can basically find this overlap, right? You know what A1, B1 are, they're related to psi 1. So can you just evaluate that overlap for me? It goes to 0. You can actually do it in your head, right? You don't have to write it out explicitly. So the main message I wanted to convey was points that are diametrically opposite in the Bloch sphere are orthogonal states. Okay, and that makes sense, right? It's basically like the north pole is basically the point where all your population is in 0, and the south pole is the place where all the population is in the 1 state, and these two in some sense we expect them to be orthogonal states, right? There is no overlap between being in 0 all the time and being in 1 all the time.
So, like you said, the dot product is telling you how much overlap there is between the vector. But why necessarily does taking the dagger of any vector, complex vector, and multiplying by another vector give you the overlap?
So I can motivate it one way. One way is simply that if I want to get the probability to be 1, right, I can't have a1 square plus b1 square. I need mod a square plus mod b square, and there it only makes sense to take a complex conjugate. That's the zeroth level answer for that. Okay, so this is how it makes sense to define the dot product this way over here. All right, so 1 minute. He raised. So is there any reason? So we motivate. So you're asking me why is there a factor of 2? Is that what you're asking me? Then you can basically represent it in a polar representation, right? So your theta goes from 0 to pi and you use the full sphere. So a point which is theta of 90 degrees is a point on the equator, and that point corresponds to an equal superposition of 0 and 1. So the factor of 2 helps in converting between that representation and a spherical mapping onto a sphere, right? So that's basically the reason. You didn't understand. So my point is that I want to map it on a sphere, okay, and for that I mark my north pole as 0 and my south pole as 1, and everywhere in between it must be some combination of the two, some linear combination of the two. And if I choose my theta as the polar angle, theta of 0 should correspond to 0, state 0, and theta of pi should correspond to a state 1, right? And then if I want to parameterize my states like this, you will realize that I need that factor of 2 in there, right? Only then if I put theta of pi, if I put a theta of pi, this becomes 90 degrees, cos of 90 is 0, sine goes to 1, and I have all my population in state 1, right? So that factor of 2 helps in mapping nicely onto the entire sphere, basically. You had a question? Forgot your question. Okay, we'll come back to it. Okay. So that's some introduction to Bloch spheres to represent two-level systems. And now I led you through all of this, and in the end, I wanted to actually talk about platforms where qubits can be realized. You remembered your question, but give me 2 minutes. Okay. So now very briefly, okay, I'm just going to say that what are the kind of applications for which qubits are useful. Why should we even care about this kind of
They actually help determine all the possible paths, and then they can find out the most efficient paths.
for what?
What? I mean,
It's a good answer in the sense that
That like for
in the first
that
case,
is
like Hamiltonian path problem.
what is a Hamiltonian path problem? So I was going to go for something more more basic or more broader, in the sense that very broadly the kind of applications that people foresee with qubits, and not just qubits. Okay, why stop at 2 levels? You can have more levels, right? So an active area of research is also the fact that what can you do with so-called objects called qubits or qubits in general, where D is d-dimensional systems, right, with like a quantum die, for example. So the point is that you can do a number of things. Okay, for example, in computing, right? In computing, you can, for chemistry, for example, has a lot of implications from quantum computing, because there are many efficient paths to encode chemical problems onto quantum computers. And the reason why modeling molecules, why is this important? So let's say I want to discover a drug for a very rare disease, okay, and then this drug has some complex electronic structure, right? The thing is, electrons are a bit complicated, okay, so they don't like to be at the same place at the same time. So there's this Pauli exclusion principle and stuff like that, and that makes numerical calculations exceedingly hard beyond small molecules. Okay, and typically if you have ever looked at the formula for a drug compound that enters in a medicine, these are very complicated formulas with hundreds of nuclei and lots of electrons and so on. So the thing is, there are efficient ways to map such problems where you have a bunch of electrons, okay, onto quantum computers, into qubits, and basically solve for the dynamics and see what are the properties of such a molecule. Is it useful for the action that it's supposed to do? That's one example. Okay, so that's something that you could broadly classify as a quantum computing goal that a lot of people like to target. And it's in some sense a noble goal, right? You're trying to solve one of the world's most pressing problems, like how do I, it need not be even medicine. For example, for climate change, I want to have some new chemical that can, reduce harmful emissions from some device. Okay, so how do I do that? Or a catalyst for a chemical process, how can I determine how to engineer a catalyst for a chemical process? All of these are chemistry problems, and chemistry problems often find efficient algorithms on qubit based devices. So that's one motivation. Another motivation is that a lot of our real world, including these molecules, but even things, other things like, for example, solid state systems. Say I want to model superconductivity. You might have heard of high temperature superconductivity and so on. Or I want to model the inner mechanism of a nucleus. Okay, say strong force, weak force, quark gluon plasma, things like this, right? You might have heard of these things if you have seen some Veritasium videos or something like this, right? So the point is, a lot of these concepts are inherently quantum mechanical, and although we have been very smart in developing classical computers, there's a limit to what you can do if I'm thinking purely in terms of either 0 or 1. Okay, and Richard Feynman was one of the proponents of this very early on, and he said basically that, well, nature is quantum mechanical, but why are your computers all classical, right? So why don't you actually build a device that itself works on the principles of quantum mechanics, so that you are able to more efficiently capture the dynamics and the behavior of the systems that you actually want to model, right? And these need not be devices that can do everything. So a device that can, say, solve a quark gluon plasma model may not be very good at solving a chemistry problem, okay, or finding the best molecule. So people not only look at general purpose quantum computers, people also try to build what are called quantum simulators. Okay, so quantum simulation is a serious business where you're trying to actually simulate a system that you really want to understand, but where you can't really put probes and actually look at the system, using another system that you can actually control, where you map the exact same dynamics onto elements that you have here, right? So it's something like a flight simulator thing, where if you don't have access to a real airplane, right, you have buttons on a joystick, and you basically mimic that. Okay, this is the gear, or this is the steering, or whatever, right? And you basically have a cockpit on your desktop computer then. So it's in similar spirit. You can make devices now that are basically very specific to specific applications in modeling very hard to model systems that you can't solve on a classical computer. So there's a distinction between a general purpose quantum computer and something called a quantum simulator that is exceedingly good at solving that one problem or that one set of problems that you really care about. Okay, so that's another set of applications. Then there is all the thing that actually started this entire business with communication, security, and so on. So you can build quantum communication protocols that are basically unbreakable by classical, by classical eavesdropping techniques. Yes.
So can you also say that they can be used to build efficient road networks or AV networks?
Yeah, so these are optimization problems, and optimization problems are hard. So that's another reason why you should care about quantum computing. A lot of optimization problems have so many degrees of freedom that solving it on a classical computer is difficult. So things like this traveling salesman problem, where there's a salesman and he has to visit a certain number of cities that are arranged on a certain graph. What is the most efficient path for this? Is it? Okay. Okay. I hadn't heard of that particular term before, so maybe it is. Not sure.
So, is it all nodes only once? We should do it all.
Ah, okay. I see. Okay. I haven't heard of that particular term. Maybe it's something I can look up. Okay. So, all right. So that's the third thing, which is in terms of communication and cryptography, that you can actually very mathematically arrive at, very rigorously, I mean, you can arrive at bounds for what is the security of certain communication protocols and so on. And finally, the thing that actually is what I work on, which is the building of quantum sensors. Okay, so the thing is, most of our current day sensors are limited by technical noise. Okay, so at some point, even if I take a ruler or a vernier caliper or whatever, right, it's limited by the resolution of the the grid lines that you have on that device, right? So if I go down and down in length scales and energy scales and so on, ultimately quantum mechanics is what, if you overcome all possible technical noise, okay, the final noise comes actually from the final obstacle comes from quantum mechanical noise. And one way to think of that noise is basically using this, for example, where I said that, if I have a uniform superposition of 0 and 1 and I make a measurement, is the state in 0 or 1, what did I tell you? The probability of getting the outcome 0 or the outcome 1 is related to the mod square, mod A square or mod B square, okay, associated with the 0 and 1. This is the quantum mechanical noise that I'm talking about. Unless you're exactly in the state 0 or exactly in the state 1, where every time you basically get 0 or 1, right? So these are basically the 2 points that you actually have access to in a classical coin. You're either always in 0 or always in 1 at the end. But in a quantum state, you can be anywhere in between. And every time you measure, there is a quantum mechanical uncertainty. It's a probabilistic outcome, right? And this is not because you did not know or you were not good enough to measure exactly 0 or 1. It is fundamentally that way, okay? So you cannot escape this noise, and that is the ultimate limit on the noise that is associated with the measurement. And there are now quantum sensors, proof of principle, not commercial, that can actually operate at that noise level, okay? And on top of this, I'm going to throw up a word that will invite a lot of questions. If I use entanglement, okay, between different qubits, we have only looked at one qubit. If I use entanglement between different qubits, then you can actually surpass the quantum noise associated with n independent qubits by using sensors that have entangled qubits as the states that you're using to measure some signal, okay? So there are a variety of applications possible with quantum technologies, and with that kind of motivation for why we should care about quantum technologies, I want to spend the next 1 hour I have talking about one particular platform, okay? Because I can't cover all possible quantum technology platforms, but I will try to give you an overview of one particular platform in the next 1 hour that I have. 1 minute, I'll get.
So with the relative phase, so you're telling only mod A and mod B give the probabilities of whatever state it is in, right? So why does the relative phase shift matter about this?
Excellent. Because what I can do is in quantum mechanics, I don't have to measure only in 0 and 1. I can choose any two diametrically opposite states, and I can choose that as my measurement basis. So I can ask for what is the probability of being in the state 0 plus 1 over root 2 versus 0 minus 1 over root 2. So these are basically the diametrically opposite points along the x-axis, okay? And the reason for that is I can do rotations, okay? So why should I map my coin 0 and coin 1 to the north and south pole? I can choose this as my north and south pole. It's a sphere, right? And then I can always choose two orthogonal basis states and measure along those basis states, right? And then relative phase matters, because in a lot of protocols, for example, in sensing, what you would do is you would prepare some superposition state, okay? And then because of some external field that you want to sense, this qubit starts moving on the equator, okay? And then it acquires a relative phase. Relative phase is absolutely crucial in sensing. It acquires a relative phase, and then what you would do is you rotate that state, okay? If it had no relative phase, it would go all the way to the north pole, but because you have some relative phase, it would only rotate partially, okay? And then you have a reduced probability amplitude of finding it on the north pole. So basically there is an interconversion between relative phase and population. In the end, what you measure is always a population. Even here, you measure a population of being in this state or this state, but you can convert your relative phase into a population. That's why it matters.
Adding on that, purely like research, talking about this from purely research standpoint, what information about the quantum state itself does the phase give?
So every every state with a different relative phase is in principle a different state. So two states with the same theta and different phi's don't have a perfect overlap, right? So what it gives you is essentially, I mean, where on the Bloch sphere it lies, right? But what's more interesting than that is, what did you do to the state that made it move from where it was on the Bloch sphere? For example, in a sensing problem, what will happen is that because of coupling to say a magnetic field or something like this, the 0 state and the 1 state will begin to acquire a relative phase. I won't tell you how, that's another story, but they will acquire a relative phase, and when they acquire a relative phase, then you moved, right? And so when I measure that change in relative phase by converting it into a change in population, I acquire information about the magnetic field or whatever that changed the relative phase. That's how you sense it. Someone had a question.
You talked before, like a few minutes back about standard qubits.
Yes.
Could you shed a little light on what linear qubits are? Because just like a few months back, there was a breakthrough in linear qubits.
I don't know what a linear. Are you sure it's linear qubit?
The Majorana one.
You're asking me about a Majorana qubit.
Yeah.
Oh, okay. That's a different story. Something that I also don't know much about. But let me just tell you the short answer, which is here we are talking about qubit in a very abstract way. A Majorana qubit is basically one particular physical realization of how you can encode a qubit. And I'm using the word encode. And what I mean by that is, let's say I have a coin. How do I encode a bit in a coin? Right. So you need some physical observable, which is whether it landed head or tail, to encode a bit, right? Similarly, you need some physical state of a system to say that this is state 0 and this is state 1. And the Majorana qubit is one particular physical encoding of a 0 and a 1. Okay, and we will look at one particular encoding in the next 1 hour. What's the plan? Is there a break in the middle, or do we just go on? Because according to the schedule I got, there was a 5-minute break or something. Okay, I need a water break, okay? So I'll just take some water and we'll continue. If anyone wants to go to the restroom or something, you're free to go. So. Yeah, just 2 minutes. Yeah, I'll just have some water. All right.
So my question, sir, how do you measure the probabilities? Because we have
I'll show you. In one particular, every platform has a different way of measuring. I will show you how this is done. Okay.
the interact with the system will collapse into either 0 or 1.
Yeah, that's what happens when you measure. When you measure, it collapses onto one of the states with a certain probability. It will collapse. That's what?
That's what the oracle does.
Yes, but again, the oracle is a black box, right? Like, meaning that it's again a mathematical object you construct. Now I'll show you how you actually do it in practice with lasers and stuff.
Every latitude has, like all the points on every latitude have the same probability.
Exactly.
So what's the point of those?
That's the question he asked some time back, which is I can rotate. No, it's fine, no problem. You can rotate. Okay, you can rotate and convert that phase. So if I have a state pointing along the x-axis, if I rotate it about the y-axis, for example, it will go up, right? Assume some sense of rotation, and with the same sense of rotation, if I have it along the minus x-axis, if I rotate it goes to the south pole, right? So I can basically measure the relative phase by rotating it into a population. So they are actually giving you information, right? So they're interconvertible if I'm allowed to manipulate the states. 1 minute. You had a question? Someone had a question? No? Okay.
So I also have a question. So why is it that you said in the beginning that our intuition does not always work at quantum scale? Why is it
Okay, why is a hard question. Okay, I don't know how to answer a why question. This is how it works, and this is also in some sense an empirical theory, in the sense that if you make these assumptions in your modeling, it always seems to give you the right results, right? So there is, I don't know if you've seen, again, this is a quote by Richard Feynman. So if someone claims they understand quantum mechanics, they don't understand quantum mechanics. So why is a very difficult question, right? So there's still a lot of research going on into, is this really how our world works, or is this, again, see, until quantum mechanics came, until we had the ability to manipulate atoms and so on, we thought our classical understanding of the world was correct. Okay, and there was, okay, that's all there was to it, this is how the world works and so on. Then Einstein came, special relativity came, we got more a different understanding, right? Then quantum mechanics came, we got yet another different understanding. So as we go to different length and energy scales that we are not used to in our current state of living, in our current lives, we get more and more insights into how the world works. So this is always an ongoing question, and I think the question that as scientists we can ask is how. Okay, why becomes more philosophical, and I'm not really sure how to answer that question, right? Okay, yeah.
SwayamPrabha. Digital India. Educated India.